Today we're going to be talking about two variable linear inequalities. So before, we've kind of talked about two different concepts that really tie into this. So we've talked about how do you graph linear equations. That skill is still going to be very important because we're going to have to know where that linear boundary line is, and that boundary line will be the same thing as graphing a typical linear equation. And we went over how to graph things like one variable linear inequalities, so something that might simplify down to x is less than 4, x is greater than or equal to 5. And when you recall, whenever we were graphing these, there were kind of two different things we had to think through. We had to think through, do we include or not include the boundary point, in this case 4 or 5, and then we also had to think through which direction do I shade. We still end up thinking through these questions with two variable linear inequalities. The difference being, though, we're not simply doing an open circle versus a closed circle for a singular point we're including or not including. We're thinking through, do I want to include this entire boundary line or not? So the notation to include or not include, that's a little bit different. Dotted if we don't include, shaded solid if we do. And then instead of thinking to the left or to the right, we're going to be thinking kind of in terms of y, where we would either shade below for less than or above for greater than. That's sort of big picture what we're thinking through. But let's dive into a little bit more detail here. So what is a linear inequality? All this is saying is that if it's going to be a non-trivial two-variable linear inequality, that means we're somehow writing a linear equation. In this case, it's given to you in standard form, but you typically would actually rewrite it sort of in slope-intercept form. And we're going to separate the different boundaries of that with either greater than or equal to, less than, or less than or equal to. Whenever we have some sort of full ordered pair, that's a solution to this inequality. So no longer singular point numbers, but full ordered pair that's a solution, then it needs to be such that when I plug it into the linear inequality, the inequality is true. So if, for example, my linear inequality was x plus y is greater than 1, the ordered pair 1, 2 would work because 1 plus 2 is greater than 1, while the ordered pair 0, negative 1 would not work because 0 plus negative 1 is not greater than 1. That's sort of all that's saying in some more language. Now, in order to talk about the solution set, it is not physically possible to list off every single ordered pair that's going to make this inequality true. There's infinitely many of them. So what do we do instead? We very, very carefully graph it. How do we graph these? Well, typically, even though this will maybe be given to you in standard form sometimes, you really want to rewrite this, if possible, in slope-intercept form. That's really what that first step is saying. Then you want to go ahead and graph that line, but then you want to keep two things in mind. If it is allowed to equal, if we are including, you're going to use a solid line if you want to include the line itself in the solution set, indicated with the or equal to symbols, whether it be less than or equal to or greater than or equal to. Otherwise, you're going to use a dashed or dotted line if you're not including the line itself, but it's simply a boundary that you're getting extremely close to but not quite touching. Then you want to think through, do I want to shade above the line or below the line? If the symbol is greater than, we're going to shade above the line because we're talking about the y's are allowed to be bigger. If it's going to be less than, you're shading below the line because the y's are smaller. Now, another thing that I think is an alternative method to step 3 that I think is even more reliable is to do a testing point and shade accordingly. And by that, I mean actually plug in a point in one of the regions that's not on the line itself, and then see, did that make the inequality true? If so, that's the region you want to shade. If not, it's not the region you want to shade. So let's actually do a concrete example here. So here, Let's say we wanted to graph the solution set to y is greater than 2/3 x plus 2. This has already been arranged in slope-intercept form, which is great. So now we're going to go ahead and first graph y equals 2/3 x plus 2. So we're going to just kind of pretend the inequality symbol's not there. So we're going to start at 2 is our y-intercept, the point 0, 2, and then 2/3 is our slope. So we're going to move up 2 over 1, 2, 3. So that would be up and then right for the positive direction, or down 2, left 1, 2, 3. Down 2, left 1, 2, 3. Up 2, and then the other one's kind of off the page. Then we need to determine if it's dotted or solid. Since it is not equal to, we're going to have to use a dotted line. Or dashed line, if you will. Dotted / dashed. Now we need to determine shading. Since it is greater than, that means we're going to be shading above the line. But I also strongly encourage you to actually pick a testing point to see if it works. So I'm just going to arbitrarily pick here the point -2, 3. Looks like it's a point that I'm saying is in the solution set. So let's actually test to see if that works. So if I'm going to plug that into the inequality itself, that would be 3 is greater than 2/3 times -2 plus 2. 2/3 times -2, -2 is secretly over 1. 2 times -2 is -4 over 3 plus 2. To do -4 over 3 plus 2, we've got to change this to a common denominator, so I'm going to do this off to the side. -4/3 plus 2, 2 is secretly over 1. We need to change this to a like denominator, so we're going to multiply both of these by 3 to make it also over 3. That's going to leave us with -4/3 plus 6/3. -4 plus 6 is 2. So this would end up simplifying down to 3 is greater than 2/3, which is a true statement, so we know that we did this correctly. Alternatively, if you want to make the algebra work out a little bit easier, it can sometimes be nice to plug in specifically an intercept. And this is exactly what this is reminding you of, that you always want to really do some type of test point to check if it works. So you want to pick any sort of point not on the boundary line. A lot of times checking 0, 0 is actually pretty easy, so I would actually recommend checking that. Easy is a relative term, but for example, in the previous problem, had I checked 0, 0, then that would have been 0 is greater than 0 plus 2, and that is false. So that would have told us not to shade below the line, because that would have been 0, 0 here, which does not work. So we don't want to shade the region that includes it. That's another way to sort of go about this just from the get-go, is just test a point. If it doesn't work, great, shade the opposite direction. If it does work, great, shade in that direction. And you sometimes are just literally testing to see if a point works. So if I could even just directly ask you, is 0, 0 in the solution set for the inequality y is less than 2x plus 1? And then you would plug that in. 0 is less than 2 times 0 plus 1. 0 is less than 1. That is true. So in that particular inequality, you know you would want to shade the region that includes 0, 0. And again, and most importantly, don't want to include something that's on the line for your testing point, regardless if it's an or equal to sign or not. If it's an or equal to sign, it's always going to work. And if it's not equal to sign, it's not going to work if it's on the line. So that doesn't really tell you anything interesting about where you want to shade. Before I go ahead and go through these examples, go ahead and try these next two on your own, and then we can compare answers. So for this first one, our y-intercept is at 0, -2, and our slope is actually 1 because there's a 1 secretly in front of that x. So we're going to go down to -2 on the y-axis. Then we're going up 1 over 1 positive direction, up 1 over 1 in positive direction. Keep on going. And then I want to ask ourselves, is this going to be dashed or solid? It's going to be dashed because it is a strictly greater than sign. It's got no line underneath. Then we need to figure out which region to shade. I can go ahead and know that since it's greater than, that means I shade above the line. And I want to double check a testing point. So if I double check with, for example, the point 0, 0, the origin is in my testing region, so I'm hoping it works. So that would be 0 is greater than 0 minus 2, and that is indeed a true statement, so I'm good. For the next one, we want to do a similar sort of process. So our y-intercept in this case is at positive 2, so I'm going to start at positive 2. Then my slope is also positive 2, so that means I'm moving up 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. Down 2 over 1 being where the over 1's to the left, so both being negative, so that's still a positive slope, versus the up 2 over 1 is where the over 1 is to the right, so again a positive slope. And then I want to use a solid line because we are allowed to equal this time, so something on the line itself is part of the solution set, such as the point 0.02. And then I need to determine my shading. Since it's less than or equal to, that means I need to shade below the line. And then I want to do a testing point to confirm my hypothesis. So for example, 0, 0 is also in this region, so I can check is 0 less than or equal to 2 times 0 plus 2. 0 less than or equal to 2. That is a true statement. I must have shaded correctly. And that's all this is sort of saying in more words, if you want this written up a little bit more carefully. So let's do some practice problems that maybe require a little bit more manipulation. So let's say you have x plus y is greater than or equal to 4. It's strongly recommended that you graph this by rearranging this to be in slope-intercept form. So I would subtract x from both sides so that I can get y by itself, so then I get y is greater than or equal to negative x plus 4. Then I want to go ahead and actually graph this. So in terms of graphing this, we're going to start at 0, 4 on the y-axis, since that's our y-intercept. Then our slope this time is a negative 1, because a negative in front of the x is the same thing as being multiplied by negative 1. So I'm going to move down 1, right 1, or up 1, left 1. Both of those would be considered equivalents. And then I need to connect it with a solid line this time. And why do I connect it with a solid line? Because it has the or equal to symbol. Now I need to figure out where to shade. This time it is a greater than or equal to sign, so we're going to shade above the line. And then I want to pick a testing point to confirm. So let's say I want to just pick the point, I don't know, 10, 0. So if I'm going to pick the point 10, 0, I'm even going to plug it into the original. So that would be 10 plus 0 is greater than or equal to 4. That is a true statement. I know I shaded it correctly. This next one, don't get too thrown off. It says graph the inequality x is less than or equal to 3. You might be asking yourself, well, where's the y value? Well, recall that x equals 3 is a special type of line. It is a perfectly vertical line. Because recall that x equals 3 means that for every single point, it is the x value 3. We want to specifically do this vertical line as a solid line because it says or equal to. Then we need to figure out where to shade. So this is a kind of rare instance where you're not shading above or below, but you're shading to the left or to the right. And specifically, since it says less than or equal to 3, that means we're going to shade to the left because all of these are x values that are less than or equal to 3. And just in case, we can still plug in a specific testing point. In this case, I'm going to plug in 0, 0. Because if I plug that in, that would be 0 is less than or equal to 3, which is a true statement, so I know I shaded correctly. You also sometimes will just be plugging and chugging in points to see if they're going to work in the inequality. So in this case, since our inequality is y is less than or equal to negative x plus 2, If we were to plug in the first point, for example, that means I'm going to replace y with -1, replace x with 3, and I'm going to get in the habit of putting that in parentheses because just in case I do plug in a negative for x, then that negative times a negative would make a positive, plus 2. -1 is less than or equal to -3 plus 2. -1 is less than or equal to -1. That is a true statement. We're good. Had that not had the or equal to sign, then that would not be considered part of the solution set. Go ahead and pause your video and see if you can check the last 3 points. So for the last 3 points, for 0, 2, that would be plugging in 2 is less than or equal to -1 times 0, which is just 0 plus 2. So that would be 2 is less than or equal to 2. That is indeed part of the solution set. For the next one, that would be plugging in 2 is less than or equal to -1 plus 2. -1 plus 2 gets us 1. That is not true, so this point is not part of the solution set. For the last one, we would be plugging in -1 is less than or equal to -2 plus 2. -1 is less than or equal to 0. That is a true statement. So 3 of them do satisfy the inequality and 1 of them does not. We can also work backwards, so go ahead and pause your video and see if you can write an inequality that fulfills these criteria. So if it's going to fulfill these criteria, we would probably be nice to ourselves and write this in slope-intercept form. So we'd have y, our slope is 2/3, so the 2/3 times x, the y-intercept is 1, so -1. It says a solid boundary line, so it's going to have the or equal to sign. Shade above the line would be the greater than or equal to sign. And then we can actually graph that. So we're going to graph our y-intercept at -1, move up to right 3, or alternatively down to left 3. And then we're going to use a solid line because it's or equal to. And then we're going to shade above the line. Then we really want to check our work still by plugging in a testing point. In this case, 0, 0 looks like a good candidate. So 0 is greater than or equal to 2/3 times 0 minus 1. 0 is greater than or equal to -1. That is a true statement. We're good to go. For this last one, he definitely requires a little bit of rearranging, but let's go ahead and do that. So if we have 2y is greater than or equal to -4x plus 10, we're going to go ahead and divide all 3 terms by 2 in order to get y by itself. So then we get y is greater than or equal to -2x plus 5. The way that we would graph that is we'd want to start at the y-intercept of 5. And then we would want to move down to right 1, down to right 1, or alternatively up to left 1, up to left 1. We're going to want to connect this with a solid line because it has an or equal to sign. And then we're going to want to shade above the line because it's greater than or equal to. And then we're going to want to pick a testing point to see if it works. So I'm just going to arbitrarily pick something here on the x-axis, in this case 10, 0. And I'm going to plug it into the original just in case I messed up some of my arithmetic. So that would be 2 times 0 is greater than or equal to -4 times 10 plus 10. -4 times 10 is -40. 2 times 0 is 0, so 0 is greater than or equal to -30. That is indeed a true statement. Now, a word of caution, I'm going to go ahead and also add on one more example here. If I had something like x minus y is greater than 2, for example. Well, when I get solving this, I would subtract x, because my goal is to get y by itself. -y is greater than -x plus 2. And then to finish getting y by itself, I would divide all 3 by -1. And when I divide by a negative for solving an inequality, that's going to flip the inequality symbol, so be careful about that. -1x divided by -1 leaves me with positive x. 2 divided by -1 gives me -2. So be very, very cautious about that. And I'm going to write this again, that if you divide by a negative, divide or technically multiply or multiply both sides by a negative. Flip the symbol. So that is a word of caution to keep in mind. And then the way that we would graph this would be just like we were graphing the other ones. So we would start at -2 as our y-intercept. It looks like in this case our slope is +1. And then we would want to use a dashed line because it is or equal to. And then for that particular one, we would be shading below the line. Looking ahead to future coursework, there is some work that's done on looking at where two inequalities overlap, as you can start to see in this image. But that's sort of beyond what is for this particular case, which is for this set of exercises, you're just graphing really one inequality at a time. But in theory, you can always graph more than one inequality on the same coordinate plane, just like we did here with this impromptu last example.